Hello, everyone, and good afternoon. My name is Janet Schatz-Snyder, and I'm from Bethesda, Maryland. And despite this very scary name to the panel, some of us can't even pronounce it, catalysis, I just learned that word, we're really going to talk about what's the future of the planet. What are the keys to solving the many energy and natural resource-related problems that we have? And of course, when you're at the Technion, you always call the number one guy Albert Einstein for your famous quote. He was the founder of the first Technion Society, and he had an idea about addressing these issues himself. He said, "The world as we have created it is a process of our thinking. It cannot be changed without changing our thinking." And that's exactly what our panelists are going to do today. The future of our planet depends on thinking differently and uncovering new ways to address global sustainability in areas such as food, health, energy, and nature. And the Technion is doing just that. We are so fortunate today to have with us as our moderator, Professor Peter Schreiner, who's right here. He's come all the way from Germany to be with us. He's a Liebig Chair and Professor of Organic Chemistry at Justus Liebig University in Giessen, Germany. My kids always make fun of me for putting accents on things, but that was actually correct German. He is president and former president of the German Chemical Society. Peter oversees a major component at the university that is focused on where chemistry becomes biology. Peter is truly a Renaissance man. He is a philosopher and a student of life and culture. He's an athlete, a musician, and a big thinker. So before Peter comes to the mic, let's meet our panelists by watching this short video.
Professor Elon Merrick is at the forefront of organic chemistry research at the Technion. The acclaimed scientist has received dozens of awards of honors throughout his successful career. Elon joined the faculty in 1997 and has held the Sir Michael and Lady Sobel Academic Chair since 2015. Most recently, Elon received the 2021 Arthur C. Cope Scholar Award from the American Chemical Society. Elon focuses a large part of his research on constructing organic molecules at the Schulich Faculty of Chemistry. He has pioneered new methods of connecting carbon atoms, which have ultimately led to drastic reductions in waste production. Elon will serve as chair of the soon-to-be-launched Center for Sustainable Processes and Catalysis at the Technion. Associate Professor Matthew Suss is changing the game when it comes to large-scale renewable energy storage and water desalination systems. Matthew joined the Faculty of Mechanical Engineering in 2014 and Chemical Engineering in 2021. Since then, he has made major contributions to the Nancy and Stephen Grand Technion Energy Program and the Stephen and Nancy Grand Water Research Institute. He is also a member of the Israel National Research Center for Electrochemical Propulsion, an Israeli delegate in the European Federation of Chemical Engineering, and an associate editor for the Royal Society of Chemistry journal, Energy Advances. Matthew's goal is to develop efficient and cost-effective flow batteries to solve some of the most pressing challenges in the energy transition to renewables. Matthew is also a co-founder of Paragon H2, which is devoted to generating clean energy and water with hydrogen technologies. Assistant Professor Charlotte Vogt is a trailblazer in the field of catalysis, a chemical process she believes is the key to unlocking new solutions to climate change. Charlotte joined the Technion in March 2021 as a principal investigator in the Schulich Faculty of Chemistry. The rising star was recently in the spotlight for cracking the case of structure insensitivity, a mysterious phenomenon in catalysis which baffled chemists for decades. Her scientific prowess is drawing worldwide attention. In 2021, Forbes listed Charlotte on its 30 Under 30 list of influential leaders in science and healthcare. Today, her main focus is on the Vogt Laboratory of Catalysis for Fuels of the Future at the Technion.
Thank you. Welcome Peter, Elon, Matthew, and Charlotte to the stage. Well done. Peter, the podium is yours.
Thank you very much, Janet, for this very kind introduction. It's a true pleasure to be here with you. I've learned so much, and I have been a fan of the Technion for many years, decades, and it's nice to be part of this session on sustainability and catalysis. I was charged with explaining to you within 5 minutes what that is. And I thought, well, I lead by example, and chemists are very practical. So when I picked up my cup of coffee and I see several coffees standing at your tables, I thought I'm going to tell you what sustainability is not. So let's look at this lid, which sort of is always something that bothered me. This lid is made from, as it says, polystyrene. It has this little triangle in here, the little arrows that tell you it's recyclable in principle, in theory. And it says number 6, which is the code for polystyrene. So they used to make the cups from polystyrene, so styrofoam, and then we were told this is no good because it can't be recycled well. So they made the cups now from paper. It makes us feel better, but we have to know that the cups are coated on the inside because the paper would dissolve. It's inside coated with polyethylene, and it's therefore not very well recyclable. Now this thing, in principle is recyclable. I checked this morning the New York authorities, state of New York, there is not a single residential facility where this material is recycled. This goes straight into the landfill. Now, the scale is important. The scale is important in particular when we look at the world population that has grown exponentially. So every second, 2.5 new babies are born. And if we scale this up with the coffee lids, this is 16 billion lids times an increasing population per year that we just store away in landfills. It is not sustainable, period. So sustainability has to do with the materials we want to use. We want to use environmentally benign materials that are cheap, readily available, and can then also be decomposed and replenished into the cycle, redirected into the cycle. Catalysis is about the energy flow that goes with this material. So this is made with a catalytic process, but I'll come into that in just a moment. Now, the exponential growth of humanity is due to lots of factors, but I think the single most important factor is chemistry, and even more so, the fact that humans have devised strategies to take what is needed to nourish the plants we eat or we feed. We take what is needed out from the air. So we take nitrogen and transform it through what is here not a cat, but a short form of catalyst. We take the nitrogen from the air, about 80% of the air is nitrogen, and reduce it, as the chemists would say, to ammonia. And that single process, the catalytic process, has enabled this growth of humanity because there's food for everybody. At least we'd hope so. And in theory, there is. Now, this process is sort of magic. It's a catalytic process and has really enabled this growth. Let me jump back here for a second. It is still a process that is not good enough. So if you know a little bit about the chemistry, we know ammonia is the first half of artificial fertilizer. You think of ammonium nitrate. This is what you put on the fields. And the nitrate component is also made from this process by reoxidizing ammonia here and then putting the two components together. So I got a call a couple of months ago from a very big industrial leader and said, Peter, we have to team up with academia again. So it's nice to see industry come back to academia and say, we got to make this process much better. Not just a little, much better. And I said, ooh, that is quite a challenge. How are we going to do, how are we going to go about that? Well, that is what these three will tell you about, and many other things. Now, if we look at the numbers for Israel, of course, these are the numbers you're interested in. It's probably already outdated in 22, so the number is much higher than that. But the projections are there will be a lot more Israelis, as there will be also a lot more Americans. And the increase in population has to be somehow accompanied with an increase in knowledge and technology. So this is quite clear. The life expectation also has increased, so everything goes hand in hand. We are challenged to feed all these people and provide good living conditions. Now, how is this done? Well, the answer is a very simple one, through science and technology. Science and technology has got us where we are, to this large number, to all these little wonderful things we have, cell phones and TVs and everything. This is science and technology, and science and technology is needed at the next level to keep us going that way and make sure that we can have the food for everybody and the processes to make all the things we need for a good life. It is a time now when science and technology are really exploding. An anthropologist would say this is sort of like the Cambrian explosion of species. Things are just developing so rapidly, so it's really important to join forces of the different disciplines to tackle the issues that are associated with feeding humankind. Now, an important aspect, this is why these three are sitting here, is to tell you that most of the things are produced, be it in the pharma industry, in new materials, and whatever, you name it, all the little things we need so badly, they're produced at industrial scale through catalytic chemical reactions. As a matter of fact, about a third of the world's GDP is associated with catalytic processes. Now, I've ramped it all up. What is this catalysis? What does this do? It's sort of the magic bullet, and it's best understood if you also understand that chemical reactions don't just happen. Otherwise, we would just implode, because we are chemical factories and it's well controlled. It's well controlled by catalytic processes. And that is because chemical reactions, when you walk home over a little hill, maybe your house is behind that hill, you have to activate yourself to climb up that hill, and you can feel how much energy you have to put into that. That's the same with chemical reactions. You have to give them a little kick, and then they can do what they're supposed to do, and you can reach your house when you put your energy into it. The magic of catalysis is that you can lower that energy that is required. So this is why I said, sustainability has to do with the material flow. Catalysis has to do with the energy flow, because it reduces the energy that is needed. So this is the energy mountain. Like there's a smaller hill to get home and get to the cold beer. So it's clearly a process that helps us save energy. And not only that, catalysis also helps you direct a reaction into the right direction. So you're not getting mixtures of all kinds of things, you're just getting one thing. It's like you go over that lower hill and you always arrive right at your doorstep and not at your neighbor's doorstep. So that's the beauty of catalysis. And the final tidbit that I should also tell you is the magic of catalysis is that the catalyst, so the ingredient that does that lowers this energy, is not used up. So it does all this matching, and at the end, it's there again, and you can use it again. And that is sustainable. So with that, I'm going to ask these three one by one. Elon to go first to explain a little bit more what the center with the name Sustainability and Catalysis entails. And then we'll go into the details, a little bit of the chemistry that's going on there to achieve these goals of having a sustainable future. Elon, stage is all yours.
Thank you, Peter. Thank you for coming. So it's a pleasure to be here and to present you the center we are planning to develop within Technion. So what I'm going to tell you today is more about the center. I'm not going to describe any of the chemistry I'm doing. I'm just going to describe what we're planning to do in this center and how we see this center. So what I would like to start with is just to tell you, coming from what Peter told you, where are we going? And to tell you where are we going, I think I have to show you where we are today. And where we are today, I have few pictures about this. What you saw from the curves that Peter showed is the world population is increasing drastically. Okay, so we are 7.8 billion citizens, and we are supposed to be 10 billions in 2050, which is a lot. So it means that if you want to keep the same life, the same quality of life, we have to produce much more. But now, to produce more has consequences. So the question is not too much how to produce more, but the question is how can we produce better? Because we cannot continue to produce as we did up to now. And I'm going just to show you in few slides where we are standing today. So here, this is something that Uri told you this morning, and this is my field of expertise, making molecules. So my job is to create molecules. And most of the chemistries I'm developing in my own research is to make, let's say, drugs. So what you have to understand that when you make 1 kilogram of a drug, let's say a relatively sophisticated drug, you have as an average 100 kilogram of waste. So we have a ratio of 1 to 100. So the question is, can we continue like this, or should we improve ourselves? Could we continue to make a ratio of 1 to 100, or to make a ratio of 1 to 10, or 1 to 5, or 1 to 2? And this is critical when you think about, let's say, this pandemic. So we had an emergency situations, and we had to find a vaccine. And luckily, science was able to provide the vaccines. But we had to provide this vaccine in billions. So the quantity is just out of mind. Okay? So the question is, of course, we had no choice, we have to produce it. But the question is, how should we produce it? And particularly that when you think about messenger RNA, which is, in fact, what you got in your body, it has 90% of a polymer which is stabilizing the messenger RNA. So we have to think about such issues and not to continue as we were used to do nowadays. Without talking about the fact that when you add this vaccine, you use syringe, which are plastics. And I think that plastic is one of the worst things that is happening in our society these days. In 1950, we were producing 1.5 million tons of plastic per year. In 2020, we are producing 350 million tons of plastic per year. When I say plastic, I mean polymers. Polymers is this, polymer is this, polymer is the lamp, our chairs. These are what we are producing. We are producing 350 million tons of plastic per year. Now, when you think about this, and when you see this bottle of plastic that we are using on a daily basis will take 100 years to disappear. 100 years, one bottle. And we are producing 350 million tons every single year. Without talking about the fact that between this stage and the stage where it will completely disappear in 100 years, we have what we call microplastics, microparticles, which are extremely toxic, which are going straight to the issue of health that we were listening this morning. And the problem is not too much to make plastics. The problem is what to do with plastics. Because the major problem of plastic is that we don't know what to do with it when it's unused. This is what Peter was telling you. The recyclability of plastic is 9%. 9% of plastic are recycled. 91%, we don't know what to do. 91% of 350 million tons per year. So this is what we are going to give to our children. So when I was listening yesterday, this morning, I was thinking because he was referring to the Center of Nanotechnology. And I was asking myself, why we are not able to make a bottle of plastics with a catalyst which will be in the nanoparticles, embedded in the bottles, and upon irradiation, you release the catalyst and the bottle disappears. Why not? It could be. We should do it. And this is a single example. I could give you hundreds of examples of situations where we are today. For instance, I can give you, let's see how this goes. Yeah, this is the Haber-Bosch process that Peter was referring to. The Haber-Bosch process is to produce ammonia. And you see, to make ammonia worldwide, we are producing 500 million tons of ammonia per year. And this is what is feeding the world. So we need it. It's not a question of to stop it. The question is how to make it. And you saw that the ammonia principle was done in 1918. And it's still the same process today. And when you are making ammonia, you are consuming 3 to 5% of the world natural gas. You are using 1 to 2% of the world energy, and you produce 1 to 2% of the global CO2 worldwide. And this is not the worst. The worst is this one. The worst is cement. It's the way to make cement has been described in 1824. In 2022, we are still using the same principle. And to make cement, and it's now, you can see this number is 30 billion tons per year. 30 billion tons of cement per year. And when you see, and it of course is used to build our houses or bridges or roads, and unfortunately with what's going on in Ukraine to rebuild hopefully very soon Ukraine. So the quantity of cement which is needed is increasing drastically year after year. And we are already at 30 billion tons. So again, to make cement is very simple transformation. You mix limestone and clay, but you have to heat at 2,700 degrees Fahrenheit. You have to heat at 2,700 Fahrenheit to make this type of transformations. And of course, when you do this, you consume 2% of the world energy, and you produce 8% of the global CO2. Meaning to make cement, to build your house, my house, our road, we produce more CO2 than any planes which are flying above our heads. Should we continue to produce cement as we do now? Or should we change it? And this is exactly the point. It's time to change our way of doing things. We have to produce, because there is no way not to produce cement, but we have to produce in a better way. And this is how came the idea, and this is the word of Albert Einstein that you heard from Janet, and what is nice with such a genius is you have sentences which fits almost everything. So this is absolutely correct. Where we stand today is coming from our process of thinking. If we do not change our thinking, we are going to give to our children, to our grandchildren, a world which will not be a nice place to live. So what we have to do is to change our way of doing things. And this is exactly why we want to develop this center of catalysis, this Technion Center for Sustainable Processes and Catalysis. And what we want to achieve in this center is to develop new catalysts, new entity which will be able to make everything we need in a more sustainable manner. So this could go from many different fields, including many different partners. And this is exactly in the main idea of our president to try to have interdisciplinary research. For instance, catalysis at Technion this is the different topics of catalysis. It could be biological catalysis, it could be with light, it could be for energy, it could be many different types. But the point is, what we want to do is to mix expertise. Issues of sustainability are issues which are global issues. And not a single one, not a single person will be able to solve it independently as we were used to do it in science. We need to mix expertise. We need to mix knowledge. So what we want to do is to have a center in which scientists from chemistry, biomedical engineering, chemical engineering, material science engineering, biotech, food engineering, biology, education, computer science, mechanical engineering, physics, electrical engineering will be at the same place. So we want to have a center which will have several layers. One of the layers will be to have equipments. And to have equipment which will allow us to understand better what we are doing. Because when we are making cement, you mix, as I told you, limestone and sand, it's easy to see what is it. But when we are talking about molecules, you have to understand what is the size of a molecule. So the size of a molecule, if you take 1 millimeter that you can see, if you divide it into 10, this 1/10 of a millimeter, you still can see it. But the size of a molecule is to divide this 1/10 into 1 million. And now we're talking about what we are doing on a daily basis. We are manipulating objects that no one can see. Okay, so we need to understand better what we are doing. We need special equipments. And this special equipment will be in this center, open to every faculty members working on catalysis and sustainable processes. It will be an open place for people working in this field, free of charge for anyone working at Technion. So this is a place where we are going to mix knowledge. And of course, we are going to tackle many different issues. So I will not go into details about all of these issues, and we have here two experts. We have Charlotte and Matthew, and you see that this is a very good example because Matthew is coming from mechanical engineering. And he does also processes which are related to sustainability, and Charlotte is working on CO2 chemistry, and of course she is in our department. So we are going to tackle many different topics, such as food, materials, energy, nature, gas, health. So every one of us will have a different place where we will be working on. And this is all the topics we have to tackle. So we have already a very large number of faculty members within Technion working on catalysis for sustainable processes. And we want to combine their knowledge and to make a single powerhouse using the knowledge of everyone. But it's not enough. And what we are planning to do is the following. First of all, we are going to have what we call design, so making new catalysts to answer all the problems I was referring to. We are going to have applications, so meaning how we can go from discovery to market. And I have already, following the discussion we had yesterday with members of Cornell and Tech, I already have an appointment with someone which was yesterday discussing about making startups in Cornell, Fernando, and I have an appointment with him in April to learn about what he did and to see how we can use it also in our systems. So design is developing new catalysts, applications will be to transfer to the real world, and education is an important component because we have to educate the new generations about sustainable processes and sustainability. So I will not go into these details because these are more or less the equipment that we need to have. I will just say maybe one word about computational chemistry and big data because nowadays there is no way to avoid to use AI, artificial intelligence, to have a better design and a better process and development of catalysts. So we are going to have a pillar of AI in this particular field. But I would like to spend the last few minutes on the last three small topics which are extremely important. One of them is industry, academia, incubators. You know, in Israel, many companies are calling me and asking me for help. And I cannot help anyone and everybody, and particularly I don't have the manpower to help all the industry which are calling. On the other hand, in this particular center, we will have the manpower and we will have the researchers. So, which means that if someone needs any help to develop a new catalyst, and he needs the expertise of Matthew, and he needs the expertise of Charlotte, which are from different fields, they will mix, they will sit, they will discuss, and they will provide mixed they will mix their knowledge to provide an answer to this company. Okay, so this is here, as I was telling you, this is how we will have startup companies coming from research lab. This is more about answering problems from industry. Now, we are well aware that to mix or to create interdisciplinary research is not easy. We are used to work in labs. Isolated labs is not easy. And this is why in this center we want to have something that we call innovative research idea startup funds. It's kind of a seed money to take two faculty members from different fields and to give them some seed money for 1 year to develop joint project, single year, different fields, to help them to have something in common, and then after to apply to grants from Europe, from Israel, from USA, wherever. So it's just to help people to mix their knowledge and to start to collaborate. So this is something we want to develop. And I would say the cherry on the cake is the last one. And this is coming from a long discussion I had with Uri. And this is what we are calling incubator of young talent. And I will take 2 minutes to tell you what is this idea. You know, when we were thinking about this center, we had the possibility to say, we are going to have a center in which we will have state-of-the-art equipment, 10 new faculty members, and it will be forever, for the next 40 years, we will have this institute. And to be honest, I didn't like the idea. So I went back to my office, I was thinking about it, and I came to the idea of having this, what we call incubator of young talent. And this is something which is unique. Not a single place in the world will have such a center. What we want to do is to have a place where we'll have only new faculty members for 7 years, until they get tenure. So we will have a place in this center under our umbrella, a very selected process to get the best of the best, la crème de la crème of every young scientist. They will be with us only for 7 years. After the 7 years, when they get tenure, they join their own department. Let's say if it's someone which is from computer science and he does AI on catalysis and sustainable processes, he will do it in this center, and then after, he will move back to his department. And it will be an open space laboratories, meaning every faculty members, we are planning to have, let's say, 10 faculty members. Each one of them will have, let's say, as an average 10 students, meaning we will have an open space with 80 students from different fields, mixing, discussing science, meaning faculty members, young faculty members from different fields will be with students, all of them will be discussing. And our hope, our dream, is, when you collaborate for 7 years until you get tenure, where you are close by, sitting with someone from a different field, but you are interacting every day, discussing with him every day about his own research, your own research, common topics. Students will learn from this PI and this supervisor and so on. At the end of the day, when the faculty member, these young fellows, goes back to his own department, he will remain in relationship with the previous one, which were in this center. So like this, we are going to create this interdisciplinary links, which is missing at the level of faculty members and at the level of students. And I see it, and it's because, as you could guess, my education is from France. I see it as a bottle of champagne. When you take a bottle of champagne and you shake it, when you open it, you have bubbles going everywhere. It's like flooding. And this is exactly what we want to do. We want to do this in science. We want to create a place where faculty members will be coming, young fellows with many brilliant ideas, tackle problems of sustainability, and after 7 years, we will take a new one. It will never be a static system. It will be constantly dynamic systems. And this is what we want to achieve in this center. And this is to my dream, this is the place where we are going to make a change, because we are going to take the best of the best and to create interdisciplinary in an open space lab with students and faculty members. This is what I wanted to tell you today. And I'm going to stop because I guess my time is over. And thank you so much.
Well, thank you, Elon, for this very vivid presentation of the center. I have one question, and that you have not answered yet. Why do you envision the Technion to be the ideal place to establish such a center?
I told you it's good. Yeah, so look, I think Elon, in his presentation during lunchtime, brought the answer. I am sitting in many committees in Israel, fortunately, unfortunately, I don't know. But in one of the committees I'm sitting, it's called the Rothschild Foundations, and I'm providing, for the last 10 years, grants to students. I can tell you, the quality of the students we have in Israel is of the highest academic level we can have. Highest academic level that you can dream of. So, up to now, most of the students were interested by computer science, electrical engineering, new technologies. And one of the reasons, and it was a little bit explained by Uri, was kind of a need. It was a need of the state of Israel. I believe that the need now is also to answer sustainable processes and to have a good answer in sustainability. And you remember yesterday, Ali Vazatos from University of Chicago told you that when he got his positions, he got phone call from students telling him, we want to work on sustainability. And so if we have a place where We have the brightest mind. It's in Israel and it's at Technion in terms of students. We will have the brightest students. And because of this, I strongly believe that this is where we are going to succeed to solve major problems.
That is a very convincing answer to me. Thank you very much, Elon. And we're going to move on to the application side. So I'm going to hear the engineer, Matthew Suss, who's going to illustrate the challenges and how he tackles them. Matthew.
Okay, thanks so much, Peter. Thanks, Elon. Thank you for having me here. I'm so excited to talk to you a bit about what I do. And I hope I give a little back because you have supported Technion so much and have enabled what I do. So my name is Matthew Suss. And I'll give a bit of a different story about the electrical grid. And so the electrical grid, as it stands today, is given by this picture over here. So what happens today is that we generate electricity at a centralized power generation station. And overwhelmingly, that is fossil fuel based. In the US, it's about 60% fossil fuel, coal, and natural gas. And then we send that electricity down the transmission lines, distribution lines to the consumer, maybe tens of kilometers as a trip. But the electrical grid is changing, and actually we see it nowadays. A few years ago it was hard to see. Now we're starting to see it accelerate in pace, which is very nice, but in a couple of ways. The first way is renewables. We see more and more renewables being integrated into the grid. In the US, it's about 10% solar and wind at the moment, and it's rising. And the question is, why can't we go entirely to renewables? How come we're at 10%? How come we can't be 100% or 50% or higher? So the issue is that these sources are intermittent, meaning if it's solar energy, if it's a cloudy day, you're generating less electricity. At night, you don't generate any electricity. So because they're intermittent, it's hard to build 100% of the grid on such a technology that doesn't provide the same energy all the time. So how do we overcome that problem? How do we increase the fraction of renewable energy? What you need to do is use energy storage. You need to store some of the excess energy during the day, for solar, for example, and then deliver it at night. So you need to time shift that energy from one time to another. Okay. That's kind of like what you do with batteries, which I'll get to soon. So that's the first change. We're seeing an increasing penetration of renewables into our grid, and that's being enabled by energy storage. We need more energy storage. The second one is, instead of electricity being generated in this big power plant far away from our homes, we can now start to generate electricity at our home with rooftop solar panels, for example, right? And I think maybe some of you even have these. But if you look at that system over here, there's this green box at the bottom. That's an energy storage system. So the system becomes economic only if you can store energy. If you're generating a lot of electricity in the middle of the day, but nobody's home to use it, everybody's at work, then it goes to waste and the whole thing is not economical. So you also need to store energy, even at the home level when you're generating electricity. And so again, the idea is that these changes in the electrical grid are being driven by changes in stationary energy storage. And I mean stationary meaning we want energy storage systems that don't go into portable devices like laptops, like laptop batteries, but we need energy storage which is stationary, which stays in one place and stores renewable energy. And that helps us grow the renewable energy fraction. So the main problem is that today's technologies are not good enough to support the growth of renewables. The main technology today is what's called pumped hydroelectric, which is basically, here's a pumped hydroelectric plant. And how do you store energy with this plant? You pump water uphill to store it in the form of potential energy. That trip is maybe hundreds of meters. And then to take the energy back, you need to let the water flow back down the hill through a turbine, and you can take the energy back. So this is really the way that we do basically 95% of the grid scale energy storage in the US. And this is not good enough, this technology, as you can imagine, especially if you want to get stuff at the home level, because the energy density is very small compared to lithium-ion batteries, for example. And so you need very big, as you can see here, big lakes, big systems, and that's not good enough for when we want to build a lot of energy storage. And you need, of course, specific geographic features. You need these lakes, you need this elevation, and so, again, not good enough. So we need better technologies. We need better storage technologies to allow us to increase the renewable fraction in our grid. So we hear a lot about lithium-ion batteries, and lithium-ion batteries are in our cars, our laptops, our cell phones. And the question is, can they also be used for this application, for the stationary energy storage application? And so that's a big question that actually is very topical, and it's helped because the lithium-ion battery prices have dropped dramatically in the past decade, from about $1,000 per kilowatt hour in 2010 to about $100 per kilowatt hour now. And that has meant that lithium may be cost-effective for grid storage. And this price drop is not because of any technology change, it's because of economies of scale. We just have these gigafactories now, and that scale allows the price to come down. But there are also some limitations with lithium, okay? And these limitations are that it's fairly expensive, relatively. Lithium is about $10 per kilowatt hour, but you could find other reactants that could serve as battery chemicals, which are less expensive. For example, zinc, bromine, and hydrogen are 3 examples of chemicals that are less expensive per kilowatt hour than lithium. So the raw chemicals can be cheaper. While lithium cycles about 1,000 times, we know that our cell phone battery lasts maybe 3 years. We charge and discharge it every day, so it's about 1,000 cycles. There are batteries based on other chemistries that are not lithium that can last 10 times as long. Okay, so instead of 3 years, maybe you can get 30 years. And that's the kind of lifetime you want at the grid scale. You don't have to replace the battery, this gigantic battery for your grid scale storage system every 3 years. That would be way too expensive. And lithium, of course, is flammable. So on a small scale, maybe we can manage with it. But on a large scale, you have to be very careful about the types of systems that you use. And safety becomes an important consideration. So what I work on in my lab is not lithium technologies, but we think actually the future in grid storage is different technologies, different chemistries, still batteries, but we call them redox flow batteries. And these types of systems, actually the chemicals which store the chemical energy of your battery, they're stored in external tanks, and you flow them through the battery system when you want to release the energy or when you want to store the energy. And that means that you can scale these systems up pretty large because the chemical energy is in this tank, and if I want a large system and to store a lot of energy, I just need to make the tank bigger, and I don't necessarily need to make the battery itself with all of its expensive materials bigger. So that's the idea behind a redox flow battery. You store the energy in tanks and not in the battery itself. Also, many of the technologies or many of the chemistries that we investigate, which are not lithium-ion, are water-based. They're not based on a flammable organic electrolyte like in lithium-ion. So they're inflammable, which is a nice feature. But there's no winning technology, meaning that lithium-ion has won the portable device market. It's the best, it's the highest energy density. And so your laptop will have lithium-ion, your car will have lithium-ion. That's the battery you're going to go for with these applications. But there's no battery that is really the go-to for stationary applications when the device doesn't have to move and when you don't need to care about energy density as much. So it's a very interesting and topical research field. But why are they not available at the moment? It's price, it's cost. Why can't we buy these flow batteries at the moment? The cost is too high. And that's where the research comes in terms of developing low-cost chemistries, low-cost systems, and then scaling those systems. So my lab at Technion is called the Clean Tech Innovations Lab, and we focus on this field of redox flow batteries. We work with several different types, hydrogen-bromine chemistry, so hydrogen gas and bromine is a reactant. That's a project funded by the EU, hydrogen air systems, which is funded by the Israel Innovation Authority, and zinc-bromine systems, which is also funded by the Israel Science Foundation. And these are all batteries based on low-cost chemistries. Zinc, bromine, and hydrogen are all relatively low cost, lower cost than lithium. So we think ultimately these technologies, as we develop them, they can become lower cost packages relative to the lithium-ion battery package. And they're all based on inflammable water-based chemistries. So there's no organic electrolytes here. So I haven't talked about catalysis yet. This is my first slide on catalysis, which is the point here. But catalysis plays a very big role in the technologies that we work on and on these redox flow batteries in general. And so now I'll come kind of full circle back to catalysis. So catalysis is a crucial part of this transition if we want to go from fossil fuels and have storage so that we can go to renewables. So for example, we work on this hydrogen-bromine flow battery. And hydrogen is, of course, we all hear about hydrogen. It's a very promising energy carrier for carrying chemical energy. And bromine actually is a chemical that's made in Israel. A third of the world's bromine comes from the Dead Sea in Israel, from Israel Chemicals. And so we work on this battery in the lab, but this battery relies on a catalyst. Okay? And the catalyst is to catalyze the hydrogen oxidation reaction. And the catalyst is made of platinum. And this is a very big bottleneck. It's a very big problem. So platinum works very well, but it's very expensive, and it's not very stable. It doesn't last as long as we need it to last. So what we need is to find catalysts that are less expensive than platinum, that work very well, catalyze a reaction, and lower that energy barrier, as Peter was referring to, well, and last for a long time. We want it to last, of course, for 10, 20, 30 years in this type of system. And that's a bottleneck here. If we want to build systems that are inexpensive, we need long-lasting, inexpensive catalysts. So I'll end there, and I'm not going to talk about the details of my research. I have other talks at technical conferences for those details, and if you're interested, we can discuss more about it. But I will basically leave it over here and just emphasize Elon's point of the important integration of this center between engineers like myself and chemists like the rest of the panel towards pushing this renewable energy transition. Thanks very much.
Yeah, thank you, Matthew, for this vivid explanation how you tackle the flow battery systems. And of course, your last slide prompts, at least for me, the question, you as an engineer, left and right chemist, industry, and several other disciplines, how would you call in expertise from the other fields to make your research better?
Yeah, that's a great question, and yeah, exactly what I ended up with here. But that's what I firmly believe, that indeed we need to all work together in the same, like Elon described. It's very important to have basically the same building that you could all work together. Because I have maybe a personal story is that there's another chemist who is actually not on this panel at Technion, who I work with sometimes on various projects, the batteries, and I didn't meet him when I first came to Technion. I actually only met him after 4 years of being at Technion, and I didn't meet him in Israel. I met him at a conference in Germany. So you know, and it always kind of strikes me because we're really complementary, and it's been a great collaboration. We've done very nice work. But what would have happened if I met him earlier? You know, if we had those extra 4 years to kind of work together. So I think it's quite important to integrate between, you know, not just chemistry, not just engineering, but to have us all under the same roof with industry together. I think personally that's very important.
Yeah, thank you very much. We're going to delve back or go back to chemistry. Charlotte, please come and tell us about how you, in your lab, tackle these specific challenges, also including the activation of very small but very difficult molecules. Charlotte, please.
Thank you very much. So I'm very excited to tell you, as Peter said, a little bit about the research that I do in my lab. And I just want to say it's been a real pleasure to get to know some of you over the past couple of days. So I'll just jump right in and say that I think that crude oil is amazing. And that's probably not something that you would expect to hear from somebody who is focusing on sustainable processes, but it's true. This is a graph that somewhat represents the graph that Peter showed in his talk, but it shows something different. It shows the gross domestic product per person for the last 3,000 years. Now, we can agree that the economy looked a little bit different 2,000 years ago, but it's also true that our global standard of living, or the growth in that, has basically been flat up to about 120 years ago, the Industrial Revolution. And in the last tiny sliver of our history, basically, we've made huge progress as humanity. And of course, there's still a lot to be done in order to have that spread out equally, et cetera, but we shouldn't discredit the progress that we've made. And I think it's something that's very optimistic to see that. And this was driven by fossil fuels. Coal and natural gas have been around for a while, but oil was discovered and we started using it about 120 years ago. I would say that this is the real driver for our expansion, or the speed of our expansion. So what's so special about oil? Oil, when it comes out of the ground, is this soup of hydrocarbon molecules. I like to think of molecules as Lego blocks. So if we talk about crude oil, the composition of the oil is very similar. There's only black and white Lego blocks, carbon and hydrogen, almost only. But they vary very much in their size. So you have smaller structures and you have bigger structures, but mainly black and white blocks of Lego with a little bit of blue, pink here and there, but mainly black and white. Part of it is are structures of about 2 to 4 carbon atoms, black Lego blocks. Part of it is about 10 carbon atoms, gasoline. 70% of oil, and this is dependent on where you get the oil, of course, in the world, is so big that we don't have a direct use for it. So we came up with a process about 80 years ago where we cut these big stretchers of black and white Lego into the pieces that we like. And the pieces that we like to work with, much like much like Lego blocks, we build our materials and fuels from hydrocarbons. So we cut these huge stretchers into the smaller pieces that we like to build our materials and fuels with. Mainly fuels, mainly energy. 90% of our fossil fuels goes towards energy and about 10% to materials, but everything is made out of oil almost. That's why I think it's so amazing. Purses, it's a one size fits all. Purses, curtains, shag rugs, epoxy, you name it. But mainly fuels, mainly gasoline, about 4 carbon atoms, kerosene, diesel, 10 to 15 black Lego blocks, and we loved our fuels. Humans and oil, it was really a love story. Until it wasn't, right? This is LA in 1950s, and the air quality was so bad in that decade and the previous that they often thought that they were under attack. They couldn't discriminate whether they were under attack or it was just the emissions from the cars, which we later found out. In 1980s, birds were dropping out of the sky. People were wearing gas masks. Your eyes teared if you walked outside. 1/3 of all people in Los Angeles had severe lung damage. 1/3. So where are we now? This is a graph showing the very unhealthy or hazardous air days qualified as where you should stay inside and close your windows over the last 40 years. And you can see in 1980, half of all days, you were told to stay inside and close your windows for your own well-being. We're at 0 almost now. But the population in LA tripled and the number of automobiles quadrupled, so it's kind of strange. What happened? I guess at this point you can guess that we used catalysts for the good. The molecules that cause smog but also cause acid rain are sulfur dioxide and nitrogen oxide. And like I said, we didn't get rid of them with a magic wand, although it does feel like it sometimes. We got rid of those 2 blocks of Lego. By the way, those are the blue and the pink that I was talking about. They're in the oil. We don't have any use for them, but if we don't take them out, they cause harmful effects on our environment. And we implemented 2 main catalytic processes that got rid of those atoms, those Lego blocks. Hydrodesulfurization is one of the other major processes in oil refinery catalysis, and we have the catalyst that most people know the word catalyst from, the one in your car, which is a 3-way catalyst. It does 3 things: converts NOxes to nitrogen, carbon monoxide, and soot, particulate matter, to CO2. And that's the next part of this story, CO2. We were able to remove the direct threat that we could feel and see and breathe and really experience, apparently, to a certain extent. It's still not great, but to a certain extent from the air. But now we have something, a silent killer, something that we can't see, something that we breathe out, but is obviously doing something. It's slowly warming up the Earth. And it's called a silent killer also because what we emit today will only have an effect in terms of, or will have its maximum effect in terms of global warming increase in about 10 years. So what we emit today, we're going to feel in 10 years, and that's scary. So we have 2 main things that we can try to do with carbon dioxide. We can try to make something useful out of it, which could be economically viable. At the end of the day, the carbon in carbon dioxide is still carbon. It's a black Lego block, and we like to build with black Lego blocks. Or we can capture it and store it, which would be a drain of energy and quite possibly money. So it's always better to have something economically viable as a chemical process, because that gives industry an incentive to do something with it, and this ends up being very important. Most likely we're going to need both. And you guessed it, we need a catalyst. But which one? Because this is something that we haven't been doing. How does it work? How do they work? How can we tune it to make the things that we want? Peter said very correctly, you want to not end up at your neighbor's doorstep. You want to end up home when you use your catalyst. And how can we make it do this pasting of black, pressing together the black Lego blocks instead of the cutting that we're used to? So this is what I do in my lab. One of the major reactions that I focus on is trying to understand how carbon dioxide catalysis works. I use special flashlights, which you can see actually here, radiation, infrared, visible, X-rays, ultraviolet light, and I study catalysts while they're working. I try to figure out their fingerprint of different catalysts and build a sort of database that contains all of this information, explaining really to the core how catalysts work in an attempt ultimately to know which knobs to turn to make something valuable. This is what it looks like in the lab. We have a lot of these big reactors, and you saw a spectrometer. So like I said, we want to know which knobs to turn to make whichever products. And the problem is, you'd expect we've been doing catalysis for a while now. Why don't we know exactly how it works? Elon already said a little bit about it. They're tiny, tiny, tiny things, more often than not, things you can't see. Many catalysts are metal nanoparticles. It's a big class of catalyst, and 3 nanometers is one of the optimal sizes for CO2 conversion, and that's about how fast your fingernail grows every second. It's really, really, really small, and it has all kinds of different sites at these 3 nanometers. So we're trying to figure out which of these tiny parts of this 3 nanometer nanoparticle does what. And slowly, slowly we're getting there. We're mapping all of the different things that happens on these catalyst nanoparticles, seeing basically where we should hit pause, and playing around with that. And we're starting to get there. These are some studies of my own which are a bit more fundamental, but we were able to tune a nickel catalyst, which is supposed to only make C1, 1 carbon atom products, to make it have 10 times more carbon-coupled catalysts. And there are people who are doing this who are actually making practical catalysts, really already getting valuable products out of CO2. But that's one thing. And it's not going to be a singular solution for CO2 and for many of the things that we're doing. We need to valorize carbon dioxide emissions, most likely in different types of processes and different geographical locations. We need to store renewable electricity, like Matt said. We need to depolymerize plastics, nanoplastics that are entering our bloodstream. We want clean transportation. We want different types of fuels. We want fuel cells, carbon neutral propulsion. And it would be naive to think that we're going to switch all of our processes tomorrow, because there's a lot of steel in the ground, we say, right? Processes are going to last for the next 10, 20 years. It would be great if we could find catalysts that are much more efficient tomorrow, and basically drop them in. And with that, I think we understand now a little bit better why catalysis is such an important part of what we do. And I want to end on a note that basically really connects to what Elon was saying. I consider myself lucky enough to have led or put together the Technion X Prize team. So I gathered, basically I sent out a flyer to the whole Technion, and I had a whole bunch of, really an overwhelming amount of students reach out wanting to join this team from every faculty: computer science, industrial engineering. I have a medicine student, and they are amazing. They're really, they make me feel lucky to be at the Technion. And we didn't continue in the X Prize competition. We actually just diverged, but we submitted our patent, an umbrella patent for multiple applications 2 days ago, after a few months. And they're very excited to build this up. So I think it's just an illustrative example of what happens when you put together people, you give them a platform to work together, and are so motivated, especially these students, to make a change. So with that, I'd like to thank you very much.
Charlotte, thank you very much. And whilst I look at this, the X Prize team seems like it's a smaller model of what's going to be the big endeavor of the center. So once you place yourself in the center, what is the most exciting thing you immediately think about?
I can only so aside from the fact that I'm a young faculty member, I just arrived at the Technion, and it takes a while for you to build up your lab. This is the reality of things. How amazing would it be that I arrived at the Technion and I have the equipment that I need on the day that I'm there? And these are all general facilities. Most of the things that you have in your lab are things that you can share. So this is a really important part of it. I would be really excited to be able to walk around and talk to my colleagues, because that's, at the end of the day, you can't put together people and make them have a good idea. Often it happens when you're having coffee, or when you bump into them and have a deeper conversation. That's where it really often, in my experience, happens. And we need a place for this. Yeah.
Very well, thank you very much. So I don't know about you, but when I listen to this excitement also that these three scientists emanate, I'm a little bit scared about the challenges. So these are big challenges, and it's pretty scary what we do with our world. That's the one side. But then what's bigger is the optimism. The optimism I can also sense, and the energy that's there. And I'm highly optimistic this is going to be a worthwhile endeavor. We're at the philosophical side, so maybe to wrap things up, I'm going to ask Ilan again to maybe sort of summarize the idea, to have a take-home message for you, while this is something that is really worth the effort. Ilan, please.
Okay, so I think that we should have a broader view of the center and the problems that we are facing. And I would like just to end up by saying something very simple. So you know that in 2 years from now, we are going to celebrate the 100th birthday of Technion. I think we can be proud of what Technion achieved for the state of Israel, for humanities in the last 100 years. But we, Technion, but like everyone in the world, made many mistakes. And many mistakes because we did things on, I would say, egoistical view. We were trying to produce for our own benefit, own pleasure. Now it's time to correct. So, there is this quote, Tikkun Olam, from Hebrew, which means we have to correct what we did and to correct the world, to have a better world. So this is exactly the place where we want to do it. And my dream is that in 100 years from now, when your grandchildren will be sitting in this room, and hopefully my child will be my grandchild will be behind the podium, we will be able to say, yes, we have been able to solve many important questions which will be very important for the benefit of all the humanities. And this is what we want to do in this center. We really want to try to solve major problems. And to solve major problems, we have to combine our expertise, we have to combine our knowledge. And we are building a center in which it will be built in how to mix knowledge at every level. Young faculty members constantly changing, constantly moving, students constantly interacting. And this is for us, for the president to read, for us, members of Technion family, this is the only possibility to solve global issues. So with this, I'm going to stop and thank you so much.